Welcome back to Know How Right Now. I'm going to do another example of a problem using Newton's second law. Let's get started. I have a particular problem here. It says a crate with a mass of 34.5 kilograms is initially at rest. A net force, or a horizontal net force of 160 newtons acts on the crate. What acceleration is produced by the net force? How far does the crate travel in 12 seconds? And what is the speed at the end of 12 seconds? Okay, so we know that there's a crate, right? Okay, we know that there's a crate here. Okay, here's some surface here. It says that there's a horizontal force. We don't know, it could be a horizontal net force. It could be a force here and a force here, maybe a force pushing it and a force pulling it. It doesn't really matter. We could even just say, well, it's just a horizontal net force. That's what it says. So let's just say it's just to make it a little more, it's a force of a pull, okay? So let's say force of pull, and we have a value for that horizontal net force, which is force of pull, which is equal to 160 newtons. Now, we know the mass of the crate, which is equal to 34.5 kilograms. Now, it says that this crate starts at a certain position and at rest, and then it travels some distance. Okay, so we know that the initial velocity is equal to 0. Alright, now, what is the acceleration produced by the net force? Okay, so what do we need to do? We actually need to draw a free body diagram. Now, let's draw a free body diagram on our little picture here. We don't have to do it this way, but it's kind of an easy one. We have the force of the pull going this way already, and then we also know that there's the force of weight right here, which is also equal to mg, and then we know that there's a normal force equal and opposite to the weight. So in other words, the crate is pushing down on the earth, and the earth is pushing back up on the crate. So now we need to figure out what the acceleration is due to this horizontal net force, which is, we just call it the force of the pull. So what do? Okay, we use Newton's second law, which says the net force of the system is equal to mass times acceleration. Well, if these are equal and opposite, we can just forget about those two. But the force of the pull is what we really want to think about here. Now, before we go any further, we want to make a direction, a positive or a negative direction for the system. And I'm going to say that going this way is positive. Going to the right, or the positive x direction, is going to be positive. Or, right. So now, let's continue. What's the net force? Well, the net force here is really, if we want to think about it, it's the weight minus the normal force, which is actually, if these two are equal, then they're actually just, they're going to subtract each other, so it's 0. So we can forget about those. We can just say the force of the pull is equal to mass times acceleration. And not only that, but you don't even really want to consider those two, because we're just trying to find the horizontal force of these two right here. Of this system going this way. So we have the force of the pull is equal to mass times acceleration. We need to solve for acceleration, so we need to solve for this here. What do? We divide we divide the mass out of both sides, and we get that acceleration is just equal to the force of the pull divided by the mass. So when we have the force of the pull, that's 160 newtons divided by 34.5 kilograms, which gives us 4.64 meters per second squared. And just to check it, I look at my units, I say, okay, well, newtons is equal to kilograms times meters per second squared. And if I want to divide by kilograms, then what do I get? Well, then I just get meters per second squared, which is what I get here. See where my eraser is. Ah, here it is. Okay, so we got that down. So my acceleration is equal to 4.64 meters per second squared. Now let's move on to the next question. It says, how far does a crate travel in 12 seconds? Okay, let's take it back to kinematics. Let's look at this object in motion, and it's asking how far will it go. Well, if you remember, we actually have a kinematic equation which says that the final position is equal to the initial position plus the initial velocity times time plus 1/2 of the acceleration times time squared. Now, it says, how far does it go in 12 seconds? So, our time is equal to 12 seconds. So, if it starts from rest, and if we say at this point, this is the origin, and this is where x naught is equal to 0, then we can say x naught is equal to 0, and since it started at rest, our initial velocity is also equal to 0. So what are we left with? We're left with x final is equal to 1/2 of acceleration times time squared. And we have acceleration and we have time, so we just plug those in, don't we? 0.5 times 4.64 meters per second squared times our time, which is 12 seconds, which is equal to about 334 meters. So, starting from rest, this horizontal force causes this box to travel 334 meters in 12 seconds. Let's move on to the next one. Let's say, let's record that here. X is equal to 334 meters. In case we need it for the next one. So notice, as I'm going along with these, with this problem, what I'm doing is, I'm putting all this information that I initially knew right here, and then whatever I solved, I continue to put that information, because sometimes in physics you get a whole lot of questions. There might be one question that has, you know, A through F or something like that, or A through J or A through K. You never know how many questions you're going to get. So then you just keep on recording your information so that you can just look back and say, oh, I've got acceleration, not a problem. I've got time, not a problem. You know, I've amassed all this information, and now it's easier for me as long as I stay organized to continue working these problems. So, what's the next question? It says, what is the speed at the end of 12 seconds? Okay, what's the speed at the end of 12 seconds? Well, I can go back to our motion equations, our kinematics, and I can say, okay, I also had a kinematic equation that said the final velocity is equal to the initial velocity plus the acceleration times the time. Okay? And if you remember, we actually have, or we can look back and we say, okay, look, our system actually, it starts off with our crate is at rest, and so here I'm going to go ahead and say, well, it's at rest, so let's make that a 0, and now what we're left with is the final velocity is equal to the acceleration times the time. And we already have all this information. We have acceleration, we have time. So we can say 4.64 meters per second squared times 12 seconds. 36, so 40, 55.7. And that's going to equal to about 55.7 meters per second. And it checks because if I take meters per second squared and I multiply it by seconds, then one of these is going to cancel out, right? And then, so we basically have this, which comes out to meters per second. So, if you have any questions about this, go ahead and post it, and I'll get back with you. I'm actually going to make a bunch of Newton's second law problems because, well, there's a lot of them in physics. If you keep on going up in physics, you'll keep on running into this classical mechanics and things like that. So, thank you for watching. Catch you later.